When we look at a modern stealth aircraft, like the B-2 Spirit or the F-35 Lightning, we might think that they become practically invisible when flying over enemy territory. For decades, the aerospace industry has sold us the narrative that through the use of classified technologies, the US has successfully built a ghost. And to a certain extent, they are right. If you look at an F-22 Raptor through the lens of a traditional X-band targeting radar, it possesses the electromagnetic signature of a bumblebee. Some countries have spent decades and billions of dollars trying to figure out the exact angles, facets, and curves required to perfectly deflect radio waves in order to avoid radar detection. But radar is only one half of the sensory spectrum militaries use when trying to detect an enemy aircraft. And there are some fundamental laws of physics that aerospace engineers cannot defeat with angle geometry or radar-absorbent paint, and thermodynamics is a big one. Flying a 30-ton aircraft at supersonic speed requires a lot of energy, which produces significant heat. The core of a military turbofan engine runs at extremely hot temperatures, hot enough to damage most metals, or the engine itself if not carefully managed. Plus, it's really hard to hide all that heat. To a radar operator, a stealth fighter might not register on the screen. But to a modern infrared search and track sensor, that exact same stealth fighter appears extremely bright on the sensors, which makes it really not that stealthy. In physics, temperature is a reflection of how fast particles are moving, their kinetic energy. So the faster atoms and molecules move, the higher the temperature. When an object is perfectly cold, at absolute zero or 0 Kelvin, even though it's impossible, atoms should theoretically be perfectly still. In the late 19th century, a physicist named Max Planck made an interesting discovery. He realized that as these atoms vibrate and collide, their shifting electrical charges emit electromagnetic radiation. Physics tells us that any object with a temperature above absolute zero must emit light. We call this black body radiation. You don't see the desk in front of you glowing because the light it emits is vibrating at a frequency far too slow for your biological eyes to process. The human eye can only detect electromagnetic waves with a wavelength between 400 and 700 nanometers. But just beyond the edge of our vision, in the wavelength stretching from 700 nanometers up to 1 millimeter, lies the infrared spectrum. This is the spectrum of heat. If you could swap your eyes with indium and antimonide focal plane arrays, the world would transform. The dark sky would not be empty. Every object would radiate a brilliant, glowing aura based on its temperature. And when using infrared detection, a military jet engine can be one of the brightest objects humanity has ever constructed. But knowing that heat emits light isn't enough. In 1879, a physicist named Joseph Stefan, later joined by Ludwig Boltzmann, formulated the equation that determines exactly how much energy a hot object radiates into the void. It is known as the Stefan-Boltzmann law. E is the total energy radiated per square meter. Sigma is the Stefan-Boltzmann constant, and T is the absolute temperature of the object in Kelvin. Look closely at the right side of that equation. The energy emitted is proportional to the temperature raised to the fourth power. In the engineering world, exponential laws are really not friendly, as we have seen in previous videos about radar jamming and submarines. If a jet engine gets twice as hot, it doesn't emit twice as much infrared light. 2 to the fourth power is 16. It emits 16 times as much light. If the temperature triples, it emits 81 times more energy. When a stealth pilot pushes the throttle forward, injecting jet fuel into the combustion chamber, the temperature inside the engine spikes from 500 degrees Kelvin to 1500 degrees Kelvin. A 3-fold increase in temperature results in an 81-fold explosion of infrared radiation pouring out of the back of the aircraft. The Stefan-Boltzmann law explains how much energy is emitted, not the type of light. For that, another law helps, the Wien's displacement law. Wien's law states that the peak wavelength of the light emitted by an object is inversely proportional to its temperature. The equation is peak wavelength of radiation emitted by a black body is inversely proportional to its absolute temperature. This means that as an object gets hotter, the light it emits shrinks in wavelength. A warm piece of metal emits long-wave infrared light, but as you heat that metal up, the wavelength gets shorter and shorter, pushing into mid-wave infrared, then short-wave infrared, until eventually the wavelength gets so short it enters the visible spectrum and the metal glows red-hot to the human eye. By combining the Stefan-Boltzmann law and Wien's displacement law, an enemy missile sees more than a blob of heat. The precision of the infrared light gives the enemy a fingerprint of exactly how hot the target is, and therefore exactly what kind of machine is hiding in the dark. When an enemy infrared search and track system, or IRST, looks up at a stealth fighter, it doesn't just see one uniform block of heat. A supersonic stealth aircraft actually generates 3 entirely distinct thermal signatures. 3 distinct signatures that the engineers must somehow suppress. The first and most obvious is the engine core. Inside a military turbofan, the combustion chamber and the spinning turbine blades are subjected to sustained temperatures of nearly 2,000 degrees Celsius. This is hot enough to melt the superalloy metals the engine is built from. The only reason the blades don't melt is because engineers use complex microscopic channels to bleed freezing air over the blades, creating a thin protective film of cold air over the metal. But despite this cooling, the metal of the engine core is very, very hot. If an enemy missile can look directly up the tailpipe of a stealth fighter and see the exposed spinning turbine blades, the aircraft becomes much easier to detect. The temperature being this high guarantees the missile will achieve an unbreakable lock. The second thermal signature is the exhaust plume. Even if you block the line of sight to the engine core, the engine must continuously expel thousands of pounds of rapidly expanding, superheated gas. This gas exits the rear of the aircraft at supersonic speeds. Because this gas is composed heavily of carbon dioxide and water vapor, both of which are highly active infrared emitters, the jet leaves a massive, glowing tail of hot air stretching for hundreds of feet behind the plane. You cannot hide this gas. It interacts with a cold atmosphere, creating a massive, turbulent wake of thermal energy. But the third thermal signature is the most terrifying because it has absolutely nothing to do with the engines. It is a product of aerodynamics. It is called kinematic heating. When you look at an F-22 Raptor, its sharp angles and smooth surfaces are designed to slice through the air with minimal drag. But at supersonic speeds, the air doesn't easily slide out of the way. As we know, air is a fluid composed of billions of nitrogen and oxygen molecules. When a stealth fighter flies at Mach 1.5, it is slamming into these molecules. At the very nose of the aircraft and along the leading edges of the wings, the air simply cannot get out of the way fast enough. The air molecules are crushed against the titanium skin of the plane, and their kinetic energy of movement is instantly converted into thermal energy. This is known as the stagnation point, and physicists calculate the temperature spike using the stagnation temperature equation. In this equation, T is the ambient temperature of the air, gamma is the specific heat ratio of the gas, and m is the Mach number of the aircraft. At the end of that equation, we have m squared, or Mach squared. This means the aerodynamic heating of the airplane's skin increases exponentially with speed. If a plane flies twice as fast, the friction heat generated on its nose and wings doesn't double, it quadruples. At Mach 1.5, the leading edges of a stealth fighter can reach temperatures of over 120 degrees Celsius, even in the freezing -50-degree ambient air of the stratosphere. And it isn't just the nose. Along the entire body of the aircraft, a phenomenon called the boundary layer occurs. The air rubbing against the skin of the plane creates immense microscopic friction. This is the problem of supersonic stealth. To survive in a modern combat environment, a plane must fly fast to evade missiles. But the faster it flies, the hotter its skin becomes. The entire surface area of the plane turns into a glowing infrared radiator. Engines, exhaust, and even air friction all produce heat, and none of them are easy to hide. And it gets even harder when trying to engineer around all of them at the same time. If the stealth plane is glowing this brightly, why isn't it shot down immediately? Why did it take decades for infrared technology to catch up to stealth? It's because of one single fragile layer of protection, the Earth's atmosphere. Infrared light does not travel well through the air. The atmosphere is filled with water vapor, carbon dioxide, and ozone. These molecules are incredibly efficient at absorbing infrared radiation. If a jet engine emits a massive burst of heat, the water molecules in the clouds and the humidity in the air act like a thick blanket, absorbing that light and scattering it before it can reach an enemy sensor 50 miles away. For early heat-seeking missiles, like the AM-9 Sidewinders used in the 1960s, this atmospheric absorption was a massive problem. They could only see a jet if they were within 2 or 3 miles of it, and only if the weather was perfectly clear. But physicists realized that the atmosphere doesn't absorb all infrared light equally. If you look at the absorption spectrum of the atmosphere, there are specific, highly defined gaps where infrared light passes through almost perfectly untouched. Engineers call these gaps atmospheric windows. There are two primary windows: the mid-wave infrared window, between 3 and 5 microns, and the long-wave infrared window, between 8 and 12 microns. If you design a sensor that looks at the entire infrared spectrum, the atmospheric water vapor blinds you. But if you tune the chemical composition of your sensor, using materials like indium antimonide or mercury-cadmium telluride, to look only at the 3 to 5 micron mid-wave window, the atmosphere suddenly becomes completely transparent. You can see the heat of a jet engine from 50 miles away, straight through the haze. And to make these sensors work, engineers had to conquer thermal dynamics on their own side. To see the faint 3 to 5 micron thermal signature of a distant stealth fighter, the missile's own sensor must be colder than the light it is trying to see. Modern infrared missiles and IRST systems actually have internal cryogenic cooling systems. They pump liquid nitrogen or pressurized argon gas directly over the sensor chip, freezing the eye of the missile to negative 200 degrees Celsius just seconds before launch. By supercooling its own eye, the missile increases the thermal contrast between the cold sky and the hot target. On top of that, modern sensors don't focus entirely on looking for a single bright dot of light anymore. Older missiles use rotating mechanical reticles to find the brightest heat source, meaning a pilot could drop a magnesium flare and the missile would stupidly chase the hotter flare. Today, IRST systems and modern missiles use focal plane arrays. These are essentially digital cameras that see in thermal vision. They possess grids of 128 by 128 or even 256 by 256 individual microscopic thermal pixels. When the missile looks at a stealth fighter, it can detect the shape of the aircraft rather than just a single heat source. It sees the hot engine, the cooling exhaust, and the friction-heated wings. It analyzes the geometry of the pixels. If a pilot drops a flare, the missile's onboard computer looks at the flare, realizes it isn't shaped like an airplane, ignores it, and continues flying toward the jet. So we have a temperature radiation law and a friction law, and cryogenically cooled enemy sensors looking through perfectly transparent atmospheric windows with digital pixel arrays. How on earth do engineers actually try to achieve stealth? The answer is thermal management engineering on a scale that is extremely difficult. Let's look at the B-2 Spirit stealth bomber. As we established, the most dangerous thermal signature is the direct line of sight to the engine core. To fix this, Northrop Grumman engineers buried the B-2's 4 massive turbofan engines deep inside the fuselage of the aircraft. But they didn't just bury them, they placed them at the end of highly curved S-shaped intake ducts. This blocks any radar or infrared sensor from looking directly down the pipe at the glowing turbine blades. But burying the engines creates a massive internal heat problem. The engines are sitting inside a carbon fiber shell, generating 1,500 degrees of heat. If left unchecked, the plane would melt itself from the inside out. To solve this, the B-2 utilizes a system of secondary air intakes. As the plane flies, it gulps down massive amounts of freezing, high-altitude ambient air. But this secondary air doesn't go into the engine to be burned. Instead, it is routed entirely around the engine core, acting as a fluidic thermal insulator. Then comes the problem of the exhaust plume. To fight the Stefan-Boltzmann law, you must drop the temperature of the gas before it leaves the plane. The B-2 uses an exhaust system known as a fluidic injection nozzle. Before the superheated jet exhaust reaches the edge of the tailpipe, that freezing secondary bypass air is injected directly into the hot exhaust stream. The cold and hot gases mix instantly, lowering the overall temperature of the plume. Furthermore, the B-2's exhaust nozzles are located entirely on the top of the wing, far back from the trailing edge. This means that an enemy infrared sensor looking up from the ground is physically blocked by the cold titanium and composite belly of the aircraft. The only way to see the exhaust is to be flying directly above the bomber.
But the B-2 is a subsonic bomber. What about a supersonic dogfighter, like the F-22 Raptor? The Raptor has to deal with massive engines, afterburners, and supersonic skin friction. If you look at the back of the F-22, you will notice the engine nozzles are not round like a traditional fighter jet. They are flat, rectangular wedges. This is not just for radar deflection. It is a thermodynamic weapon. A traditional round exhaust nozzle creates a thick, cylindrical plume of hot gas that takes a long time to mix with the cold atmosphere. By crushing the exhaust through a flat rectangular nozzle, the F-22 forces the hot gas into a thin, wide ribbon. This increases the surface area of the exhaust plume, allowing the freezing ambient air of the stratosphere to rapidly mix with and cool the gas within milliseconds of it leaving the jet. The thermal signature is sheared apart by the slipstream before it can form a massive glowing tail.
To deal with the supersonic skin friction, the F-22 relies on heavily classified thermodynamic materials. The composite skin of the aircraft is designed to act as a heat sink, rapidly absorbing and dissipating the kinetic heat generated at the stagnation points on the nose and wings. The jet fuel itself is heavily utilized as a liquid coolant. Before the jet fuel is burned in the engine, it is pumped through a labyrinth of heat exchangers located throughout the wings and fuselage. The cold jet fuel absorbs the heat from the plane's avionics, radar, and skin friction, and then carries that heat into the engine where it is finally burned. The fuel system serves as the aircraft's circulatory cooling system. But despite all of these brilliant engineering solutions, there is one more issue. As we covered, to be stealthy against radar, a plane must be coated in radar absorbent material, or RAM. This material is made of microscopic iron ferrite particles suspended in a polymer matrix. When an enemy radar wave hits this material, the electromagnetic wave induces a microscopic alternating current in the iron particles. But energy cannot be destroyed. It has to go somewhere. The RAM absorbs the radar's electromagnetic energy and physically converts it into thermal energy. The plane absorbs the radar wave, and in doing so, gets hotter. Furthermore, radar absorbent materials are, by their chemical nature, incredibly effective thermal insulators. Think of them like a thick, rubbery blanket wrapped around the entire airplane. While this blanket stops radar waves from bouncing off the metal hull, it also traps all the internal heat generated by the avionics, friction, and engines inside the aircraft. It's really ironic that the very material that makes the aircraft invisible to radar makes it more difficult to shed heat into the atmosphere. It is a trade-off you can't avoid. If you want to defeat the radar equations, you must worsen the thermodynamic equations. There are limits engineers can't get around.